Okay, I'm going to do my best to talk through a summary of what we covered in the first quarter, starting with functions. So the basic concept of a function is it's a way to map an input to an output, right? So if we have a function like f of x equals 2x squared minus 5, there's some operations that are happening to x that are going to map it to an output. So if I do f of 2, no, let's do f of 3, right? That means I'm going to do 2 times 3 squared minus 5, right? So what's happening is we're going to do 3 squared, which gives us 9, right? And then we're going to take that and we're going to multiply it by 2, right, which gives us 18. And then we're going to subtract 5, which gives us 13, right? So we do 2 times 9 minus 5, which gives us 18 minus 5, which gives us 13. So what this function did is it mapped 3 to 13. Okay, and it will map other inputs to other outputs following these operations. So then we covered that you can determine an inverse function by taking all the operations that happen and undoing them. So again, the operations that are occurring are we're squaring, we're multiplying by 2, and we're subtracting 5. So to find the inverse function, we can find the inverse operations. We're going to plus 5, we're going to divide by 2, and we're going to square root. And because we're mapping the output back to the input, we have to undo the operations that they happen in reverse order. So when we make this inverse function, f inverse of x, which we denote like that, we're going to do x plus 5 first, and then we're going to divide by 2, and then we're going to square root. Because before we squared, then multiplied by 2, then subtracted 5, so we're going to undo those in the reverse order that they happened. And now we see we have our inverse function, and since our function mapped 3 to 13, we should be able to map 13 back to 3 by plugging 13 into the inverse function. So we get the square root of 13 plus 5 divided by 2, which is the square root of 18 divided by 2, which is the square root of 9, which equals 3, right? So the inverse has now taken 13 back to the input 3, so inverses switch inputs and outputs, okay? And we also talked about how you can compose two functions. So if I have f of x as my function still, and that's 2x squared minus 5, and I have another function, g of x, which will say g of x equals the cube root of x minus 2. What we can do is we can do a function like g of f of x, where we take the function f of x and we plug it in to the function g, right? So wherever we see an x value in the g of x function, we're just going to replace that with the entire f of x function. So instead of writing x, I'm going to write 2x squared minus 5, right? And then we still have the minus 2. So then our final composed function would just be the cube root of 2x squared minus 7, right? We can also do the reverse and plug g of x into f to get f of g of x, which means that we would take g of x and just plug it in as our x value for f of x. All right, we also talked about transformed functions, and I'm just going to talk about this through drawing a random graph here. Let's say that this is our function f of x, right? And then let's say we want to transform this function. So maybe we want to transform the input. So it's now x minus 5. And then maybe we want to vertically shift it by 3. What this is going to do is it's going to shift 5 units right, and 3 units up, right? So if I want to draw my transform function now, what I'm going to do is maintain the shape, but just shift it 5 units over and 3 units up. So I'm just obviously just sketching here, so it's not going to be perfect, but I've moved it up and over, right? To the right, 5 units, and up 3 units, right? So we did this through a couple different, using parent functions like x squared, which looks like this, right? Here's our x squared function. Okay, and then maybe we, like a question you would have been asked to do would be like sketch the function x plus 2 squared minus 5, right? And then that means that we're going to shift it over 2 and down 5. So then we move all those points over 2 and down 5, and then we have our transform function now. Okay, so maybe you can review the other types of transformations we did by looking back at your notes. You can do vertical flips, right? We can also flip vertically. We can make it steeper, or we can make it less steep by multiplying by a factor out front, right? So maybe you can review those other transformations that we covered by looking at your notes. Okay, so then types of functions we talked about were like polynomials, right? So we reviewed end behavior of polynomials. Polynomials just have multiple pieces, right? X to the fourth plus x cubed minus 5x squared minus 2 maybe, or another example of a polynomial would be like 3x squared minus 2x plus 5, or another example would be 3x to the fifth minus 2x to the first minus 3. Right, and we talked about the different possible end behaviors you can get, and you should just try to remember this yourself. We could get end behavior of down up. What conditions lead to that end behavior? We could get an end behavior of up down, or we could get an end behavior of up up or down down. And what we mean by end behavior is literally what's happening at the end of the graph. So here's an example of one that has a down up end behavior. Okay, here's an example of one that has a down down end behavior. And based on the structure of the polynomial, you can determine the end behavior. So you try to remember what we need to look for in a polynomial that will lead to these different possible end behaviors in our graphs. We also talked about rational functions. So rational functions where we have a variable in the denominator. So maybe we have a polynomial in the numerator and we have a polynomial in the denominator. Right? This is a rational function. And we talked about different key features of rational functions, and through the method of having a function where it just works out that it factors nicely on the top and the bottom, so you can have the rational function in factored form and then determine some key features, right? So we may have had a function that would factor down to something like this times x minus 6, and then maybe that's divided by 5 times x minus 2 times x plus 1 times x plus 3, right? And then we immediately see that we have some matching factors on top and bottom. We have some factors that only appear in the top, and then we have some factors that only appear in the bottom. And so we can use this to identify our holes, our x-intercepts, and our vertical asymptotes, right? Looks like we have some vertical asymptotes at -1 and -3. Okay, we have an x-intercept at x equals 4 and x equals 6. And then we have a hole that happens at x equals 2. And a hole is like a missing point, so we need a coordinate to show where the full missing point would be. So we need the y value. And recall that what we can do is just cancel this x minus 2 factor that's not affecting the shape of the graph, but is causing the hole. And then we can just plug in our x value. So we would get 2 minus 4, 2 minus 6. Okay, can't forget that we have a 3 out front as well. And then that would be divided by 5 times 2 plus 1 times 2 plus 3, right? So then we have 3 times -2 times -4 over 5 times 3 times 5. So what does that give us? That's -6, positive 24 on top. And then on bottom we have 75, right? So our hole is at 2 comma 24 over 75. Okay. We also talked about how to find horizontal asymptotes and those rules. So we have that we have a degree 3 polynomial, 1, 2, 3, 3 factors over a degree 3. It's matching, so it's just going to be whatever's left out front here. So we would say that there's an HA at y equals 3/5, right? And then you can also find the y-intercept by plugging in x equals 0, right? And that'll determine the y-intercept. And then we can use all these key features to reasonably sketch a nice graph of this function. Okay. So then we got into limits, and we first started by just talking about limits on a graph. So we may have looked at a graph that looks something like this, right? And maybe this is x equals 1, and this is 1, 2, 3, 4, 5. Okay, so we talked about and we'll call this the function f of x, and we talked about this notation of doing the limit as x approaches 1 from the left of f of x versus the limit as x approaches 1 from the right of f of x. And that means that we go to our graph and literally approach that x value from either the left or the right, from the negative side or the positive side. So we're going to see what happens to our graph as we approach 1 from the negative side, the left side. It seems like our graph is approaching 5. So we would say this equals 5. Okay. And then what if we approach 1 from the right-hand side? Okay, 1 from the right-hand side is approaching 2, right? And then if you see this notation of the limit as x approaches 1, just without a positive or a negative, that means you have to approach from both sides. And if you approach from both sides and you're approaching something different, like we are in this case, 2 and 5, we would just say that this limit is not equal to anything. It just does not exist, dne. All right? Whereas if we were to do the limit as x approaches negative 3, okay, from the left and from the right, we're approaching the same hole here, but the graph is approaching an output of 1, so we would just say that this limit is equal to 1. So the basic idea of a limit is it's showing you what happens to y as we approach a certain x, right? So what happens to y as we approach a certain x? What happens to y as we approach a certain x here is what's happening to y is it's approaching 1, okay? What happens to y as we approach 1 from the right is it's approaching a value of 2. So that's the basic idea of limits, and then what we do is we use these to calculate instantaneous slope. So first we need to remember what derivatives are and what instantaneous slope is. So if you just draw a straight line, that line always has the same slope. It has the same rise over run consistently. But if you draw a curve, that curve has a constantly changing slope, right? The slope right here is different from the slope right here, is different from the slope right there and right there. Okay, the slope is always different. But what we can do is we can zoom in until this starts to look like a straight line, because straight lines have slope and we can calculate their slope by doing the change in rise over the change in run. So the derivative tool helps us calculate instantaneous slope at every single point on a curve. And the method that we covered for doing this is, I'm just going to draw a different graph here. Okay, what we would do if I wanted to say, let's say I wanted to find the instantaneous slope of this function, this graph, at that point, right? Well, what I do is I can take another point just on this graph, and then I can draw a line between them. And remember that this is called a secant line. Okay, and then so let's say that this is happening at x equals a, and this is happening at x equals b, and this is the function f of x. Okay, what we need to do to calculate the slope of this line is do the change in rise over the change in run, right? And this is going to give us the slope of our secant line, otherwise known as the average slope or the average rate of change. That's just my cat meowing in the background. Don't mind her. Okay, so slope of secant line. So what we want to do if we want to find the instantaneous slope at x equals b is we want to take these 2 points and let them become really close together. So if I take that point at x equals a and I move it here and then move it here and then move it here and keep moving it closer to b, now when we draw that line between them, it's going to start to look more like what we call a tangent line. It's going to go through just the red point because the red and the green point are so close together that we can treat them as one point. So how we did this for a specific function is, like, let's say we have a function like f of x equals x squared, and we want to find the slope at x equals 2. What we did is we would say, okay, well, let's find the slope between a moving point. We can just call it f of a. Well, let's call it f of b. F of b minus f of 2 over b minus 2, right? So really what we're doing here is this is b squared minus 2 squared over b minus 2, right? And then what we did is we said, let's take a limit as b approaches 2 so that the 2 points become really close together. And then we were able to accomplish this in Desmos by making b a slider. Okay, and then you could let b equal like 1.999. You can say 1.99, but just make it something really close to 2, and that gave us an approximation of our instantaneous slope. Okay. So then finally, we talked about there's a pattern we discovered by calculating a bunch of instantaneous slopes. So we found out that if we have a function that is a polynomial with real number exponents, then the power rule says the derivative f prime x is just going to be equal to, we just multiply the exponent by the coefficient and then subtract 1 from the coefficient. And then if you have a constant value, the derivative of that is just going to be 0. So that goes away. So then this is our function that's going to tell us the slope of f of x. So if I want to know the slope at x equals 1, I'm going to do f prime 1 equals 9 times 1 squared minus 4 times 1, which is going to give me 9 minus 4, which tells me that the slope of my function is 5 at x equals 1. Okay. And so we also did power rule involving like an exponent in the denominator and also with like a radical. So that's something that we're going to have to review as well. But that's just the basic power rule. Okay, finally we can talk about visuals. So if this is f of x, we want to remember that f prime x describes the slope of this. So we can notice that the slope of this graph is 0 at these maximum and minimum values because the tangent line is flat if we draw the tangent line to the curve. So what we can say then about the derivative is there must be an x-intercept because the slope is 0, so the value of the derivative is 0, which means there's an x-intercept wherever there's a max or a min. And then we can see that this function starts by decreasing, so the derivative must start as being negative to show that it has a negative slope. The function has a negative slope until there where it's flat. Now it has a positive slope until there, and then it has a negative slope again. Okay. This video is already long enough, so that's good for now, and we'll get back into some new material now.